Hello friends, welcome to the channel of Digital Tutorial. Today we are going to discuss about Booth's multiplication algorithm. आज हम किसके बारे में डिस्कस करने वाले हैं? About the Booth algorithm. So what is Booth's multiplication algorithm? What it does is that it does the signed binary integer multiplication in 2's complement form. It does the multiplication of signed numbers in 2's complement form. For example, it can do the multiplication of 7 into 3. Both are positive number. It can do the multiplication of 23 into minus 9, where 23 the multiplicand is positive and minus 9 the multiplier is negative. It can do the multiplication of minus 7 into 3, where minus 7, that is the multiplicand, is negative and multiplier is positive. It can do the multiplication of minus 7 cross minus 3, where multiplicand and multiplier both are negative. Now, slowly I will go through the flow chart of the Booth's multiplication algorithm. First we will start the algorithm. Then A is a variable. I will initialize it to 0. A is a accumulator. M stands for the multiplicand. Q is a variable that will contain the multiplier value. Qn minus 1 is 1 bit, which is 1 bit lower than the LSB of the Q. Means if Q0 is the LSB of the multiplier, then Q minus 1 is 1 bit lower than the LSB, and then this variable I will initialize it to 0. Count is the sequence count. It will tell us how many times the loop of the algorithm has to be run, and I initialize to the value n, where n is the number of bits of the multiplier. Now, Q0 and Q minus 1, if I put them next to each other, then that means if I concatenate it, I put them together and the value comes as 0, 1, that means what I have to do? I have to update the accumulator in such a way that accumulator value will be the older value of accumulator plus m, that is the multiplicand. If this value comes as 1, 0, then how I will update the accumulator variable? I will update the accumulator variable with the old value of a minus the multiplicand value. Now, if Q0 and Q minus 1 are both same, either 0, 0 or 1, 1. In both the cases, what I will do? I will do the arithmetic shift operation. Right shift operation will happen of A, Q, Q minus 1. All put together, A, Q, Q minus 1. Arithmetic right shift operation. When the Q and Q minus 1 are 1, 1 or 0, 0, in either of the cases, we will not follow this loop. We will directly go and will do the arithmetic right shift. But if Q0, Q minus 1 falls in any of the two categories of 0, 1 or 1, 0, I will do first updation of the A here also and here also, and then we will go to the arithmetic shift operation, right shift operation. We will go here and we will do arithmetic right shift operation of A, Q, Q minus 1. Once this step is done, we will go to the next step where the counter is decremented by 1. Counter was initialized to n. Now counter is decremented by 1. Then continuation of the earlier this flow chart only. Okay. If the after count is equal to count minus 1, A it is not equal to 0, then what I will do, I will repeat this loop. I will go here. Again I will check for q minus 1. I will check whether it is 1 0 or 0 1 or either of these two cases. I will follow this route or I will follow this route or this route, and again I will do the count equal to count minus 1, and here I will check the value. If it is 0, then I will end it. Flowchart will be ended, loop will be ended. Else if it is no, I will again do the checking. Okay, you understood, no? The loop will be run for n times number of bits of the multiplier, and once it is n, we will go out of the loop and we will check for the value of a and q, and they will together give us the multiplication value. Okay, so this one is the flow chart for Booth's algorithm. Now in tabular form, I want to show the step 1 where I am doing the checking of q0 and q minus 1. It is not qn minus 1, rather minus 1. So if it is 1 0, then a will be updated with a minus m value. The multiplicand is subtracted from the partial product upon facing LSB equal to 1 in multiplier. So if the q0 is 1 and q minus 1 is 0, then we will go to this step, and the partial product, this one, this a, actually the accumulator only contain the partial product value. It is called partial product because of the reason that at the end a and q value will only determine the product of the multiplication. Okay, so every time we are updating the a, the accumulator value, so it is called the partial product. So the multiplicand is subtracted from the partial product upon facing LSB equal to 1 in multiplier. Hope this much is clear with you. Now again I am checking, that is the, here please note it is q minus 1, okay, q0 and q minus 1. If it is 0 1, okay, that is means the LSB of the multiplier is 0. So a will be updated a plus m. The multiplicand is added to partial product upon facing the LSB equal to 0 in multiplier. Means here is the multiplier LSB value, this is 0. Q minus 1 is 1 bit lower than the q0, okay, and it is 1, okay. At that time the updation of a will happen, the partial product, this a, the accumulator contain the partial product, it will be updated in such a way that a is equal to, a will be holding the old value of a plus m, the multiplicand value. Okay, now 0 0 or 1 1, when q0 and q minus 1 are both same, 0 0 or 1 1, in either of the two cases there is no change in the value of partial product, a will hold the old value only. Okay, the partial product does not change when the multiplier bit is identical to the previous multiplier bit. This is the previous multiplier bit, q minus 1. Actually, why it is called previous multiplier bit, you will understand how q minus 1 is getting updated every time when we go through the arithmetic right shift operation. So every time it will hold the q value, q0 value, okay, q minus 1 will hold the previous q0 value, okay, after going through the loop. And in the beginning q minus 1 is initialized to 0. Now here we will do the step 2. So we did the updation of a. Okay, a is updated in either of the three cases. If q0 and q minus 1 is 0 0, 0 1, 1 0 or 1 1. After that step is over, arithmetic shift operation right is happening. So there a, q minus 1 all put together next to each other. Okay. Please note here right shift will definitely happen. So every time every bit Suppose it is 0, 1, 0, 0, 0, 1, 1, 0 and it is 0. Right shift is happening. 0 will come here. This 0 will come here. 1 will come here. This 1 will come here. This 0 will come here. This 0 will come here. Then here it would be 0. This will here. This one here. This one here. Now here the MSB of the A will hold the sign bit. So it is the same bit. The MSB of the A will be same as the older one. This is 0 only because it holds the sign bit. Okay. So this one will not change. This I am keeping same. So that is what it is said. Please note sign bit in A remain unchanged during this right shift operation. Okay. When the right shift of the partial product and the multiplier value including the q minus 1 is happening, please note during this right shift operation the MSB of the updated A would remain same with the value of MSB of older A. Now we will go through the step 3. Here what we'll do? We are doing the decrementation of the count value. So already I have shown you in the flow chart how the decrementation is happening, where we are doing count equal to count minus 1. Sequence counter is decreted and every time we are checking the count value if it is 0 or not. When it is 0, the loop is ended, the flow chart is ended. If it is not equal to 0, again we are checking the updated value of Q0 and Q1. What I have said, repeat the loop n times till the time count is equal to 0. You have to keep repeating the loop. N is equal to the number of bits in the multiplier. Now let us see an example, okay, where I will multiply minus 3 with minus 7. Minus 3 is the multiplicand, minus 7 is the multiplier. Minus 3 is negative, minus 7 is negative 2. We will multiply them using Booth's algorithm and we will see the result. Okay? Whether it is equal to 21 or not. We know minus 3 multiplied by minus 7 is 21. So let's go through the loop of Booth's algorithm and get to see whether we get the correct result or not with the algorithm. Now minus 3 and minus 7 are both negative. So 2's complement of 3 is actually minus 3. So 2's complement 3 is 1's complement of 3 plus 1. 1's complement of 0, 0, 1, 1 plus 1. What I get? 1, 1, 0, 0 plus 1, 1, 1, 0, 1. So, on doing the 2's complement, we will get the result of, on doing the 2's complement of 3, I will get the binary value 1, 1, 0, 1. It is the negative value of 3 only. Now I will do the 2's complement of 7 and that actually gave the minus 7 value only. 2's complement of plus 7 is 1's complement, 0, 111 plus 1. So that is 0, 111, 1's complement. If we do, 0 becomes 1's and 1 becomes 0, 1 becomes 0, 1 becomes 0. 1, 000 plus 1 is 1001. So 1001 is the 2's complement of 7 and that is equal to minus 7 value. Initially A is put as all zeros, Q is put as 1001, multiplier M is equal to 1101, multiplicand. So it was minus 3 into minus 7. Minus 3 binary value is the 2's complement of 3. That we got is 1101 and minus 7 is the multiplier. 2's complement of 7 gives the value of minus 7 in binary, that is equal to 1001. So a minus m can be put as a plus bracket minus m. Okay, bracket minus m means what? When we want to do a minus of a binary number, then we have to get the 2's complement of the positive number that will give the minus of that number. So if I want to get the minus of m, what I need to do is I need to do the 2's complement of m, and 2's complement is what? 1's complement of m plus 1. So a plus 1's complement of m plus 1, and I can put it like this: a plus m bar plus 1. M bar is the 1's complement where all the bits are inverted. Q minus 1 is initialized to 2. We know that minus 3 and multiplied by minus 7 is 21. So let us see how the final value 21 is stored in A and Q. So A and Q together will store the value of product of minus 3 and minus 7, that is the multiplicand and multiplier. We will see how it happens through the Booth's algorithm. Now I have made a table. Okay. Now see, the initial value of A is all 0, Q is 1001, Q minus 1 is 0, and count is 4. Number of bits of multiplier is 4, and 1001 is the 2's complement of 7, so it is minus 7 value. Now your table, you see there are 5 columns: 1, 2, 3, 4, 5. First one gives the operation, second ones give the accumulator value that will hold the partial product, Q will hold initially the multiplier value, Q minus hold initially will hold the 1 bit lower to the LSB of the multiplier, and count will hold the number of counts. On this count value will determine the number of times the loop has to be run, where we check for Q0, Q minus 1. So initially it was like this. So if I put, you see, I have done the explanation here. I have put everything together: A, Q, Q minus 1. You see, LSB is 1 and Q minus 1 is 0. So 1, 0. That means I have to do the operation A plus M bar plus 1. So A is coming as all zeros, plus M bar is 0, 0, 1, 0. Please note M was 1, 1, 0, 1. If I negated all the bits, so it would be 0, 0, 1, 0. So that is what? So M bar is equal to 0, 0, 1, 0 plus 1. If I do, then I will get the updated value of A as 0, 0, 1, 1. Okay. So the now new value of A, Q and Q minus 1 would be 0, 0, 1, 1, 1, 0, 0, 1, 0. Now I am doing the arithmetic right shift. Okay. 0. This 1 will come in this position, 1. Just it is shifted in a left hand side, no. So the right shifting I am not able to show it properly, but I will try to point it out for your understanding. So 1, this will come here at the Q minus 1 position, 0 will come here, 0 will come here, 1 will come here, and this one will come here. These are the 4 bits. Now it will form the Q. This one will come here, this 0 will come here, this 0 will come here, and the same this 0 will come here also, because the sign bit of A remain the same. So this one is now the updated value of A also 0001, same as the MSB of 0011, that is the A. Okay, sign bit remain the same. 2 steps. Okay, A equal to A minus M, that is A plus M bar plus 1, and this arithmetic shift right, both these things I will show in the table. So in the table, after the first loop run, a plus m bar plus 1 value were coming as 0 0 1 1 1 0 0 1 0, and arithmetic shift right was coming at 0 0 1 1 1 0 0 1. Count equal to count minus 1 we did, we got the 3 value. 4 minus 1 3, so it is not 0. So again the loop will be run. So you check, you see here step 2, here 0 0 1 1 1 0 0 1 0 1, a equal to a plus m coming as 1 1 0. Okay, again I am doing the arithmetic shift right. So 0 0 1 1 0 1 1 1, and this one is same as 1 because it will contain the MSB of A. Okay, so the updated value of A q minus 1 is all 1, 4 ones, 0 1 1 0 0. Count equal to 3 minus 1 equal to 2. So we have updated it in the table. A equal to a plus m and a SHR. These two steps I have shown here. Now we will, here it is 2, no, not yet 0. So we have to run the loop again. That I will show. Steps 3 you see, a q minus 1. So q0 and q minus 1 are both 0 0. So no updation of a step will happen. We will directly go to ASHR step, arithmetic shift right step. And after shifting it, we are getting all ones, all 4 ones, 1 0 1 1, that is of q, and q minus 1 is 0, and count 2 minus 1 is 1, not yet 0. Okay, we will update it in the table. Here you see, after the 2 step, again arithmetic shift right has happened, and this one, all 4 ones, 1 0 1 1 0, this step has happened and count has become 1. So it is not yet 0. Again I have to run the loop because q0 and q minus 1 is 1 0. I have to do the a plus m bar plus 1 step, that is a minus m. You see, that is the step 4, all ones, all 4 ones, 1 0 1 1 0. So a is equal to a plus m bar plus 1. I am getting as all 4 ones, that is a plus m bar was coming as 0 0 1 0 plus 1. So 0 0 1 1, on adding them up I was getting 1 0 0 1 0, but the register A will contain, this variable will contain only 4 bits. So the most significant bit I will discard it, and the value will be 0 0 1 0. Okay, the A value. So 0 0 1 0, 1 0 1 1, 1 0 1 0 1 1, and 0 value. I am doing the arithmetic shift right, and I got the value 0 0 1. This is the arithmetic shift right. So 0 0 1 0 1 0 1 1, and count is coming as 1 minus 1, that is equal to 0. Now we got the 0 as the count. So no more loop will be run. In table I have shown it. A plus m bar plus 1, 0 0 1 0, 1 0 1 1 1, and ASHR value is coming as 0 0 1 0 1 0 1 1. Okay, and this value is actually 0. Count value has come as 0. Note from the table, A and Q value at the end as coming as 0 0 1 0 1 0 1. 0 0 1 0 1 0 1. So the binary value of this is coming as 2 raised to 0, 2 raised to 2, 2 raised to 4. On adding them up, I am getting the 21 value. Okay. So answer is minus 3 multiplied by minus 7 is equal to 21. If you like the video, share with your friends. Please subscribe the channel and have a very nice day.